Awesome. Thank you, Dr. Garvey, for that introduction. So today, like Dr. Garvey said, we're going to talk about temporal and spatial changes in habitat quality for silver carp and native planktivore fishes. So to quickly start out with a overview of how the talk is going to go today, we're going to start with a broad introduction that's going to encompass both chapters, then move into chapter 1 that's going to include a brief introduction, methods, results discussion, and then we're going to move into our second chapter following a similar pattern as chapter 1, then move into our final conclusions, and then finish up with our acknowledgments and questions. So to start, large rivers are important for recreational opportunities such as water sports or fishing, commercially for moving large amounts of raw material throughout the country, but also ecologically in that there are a unique set of interactions and unique species that occur within these large systems. So for the sake of this talk, we're going to focus more on the ecological side of large rivers. So large rivers also have different spatial and temporal variability scales, such as large scale and short scale changes. An example of maybe like a large scale temporal changes might be water level. So what we see in this picture on the right is the river spending well over its bankful width into the floodplain habitat in one section of the year, as where in another section of the year the river is well below bankful width, exposing potential hazards. So through this large-scale temporal variation, you can see a difference of water levels within these large rivers, but also discharge. For example, this would be maybe in the springtime after a major snow melt. Water discharge is going to be higher than compared to late summer, early fall, when typically drought occurs, to where discharge might be lower. An example of maybe like a large scale spatial changes might be in one section of the river, there might be a high degree of habitat heterogeneity, meaning that there might be a wide variety of different habitat types, such as like a channel border with a side channel with a thalweg habitat, as where a couple river miles up or downstream of that location, the river might be more channelized and not have a wide variety of habitat types available. Short-term changes might be temperature. So these changes would occur probably within a day. So what we would see is in the later afternoon, water temperatures might be a little bit higher than first thing in the morning. And then short-term spatial changes might be, like an example of this would be water velocity, to where the main thalweg may have a certain water velocity, is where a very close or adjacent habitat type is like a channel border might have a different water velocity persisting within that habitat type. So invasive species have ecological and economic impacts on their invaded areas, and they have seen to cause decreases in biodiversity, and the economic costs associated with their damages they inflict have increased substantially over the past 60 years, ranging from around $2 billion in the 1960s to around $26 billion in 2010. And there is an increased presence of invasive species invading our large rivers in the United States. But large rivers are also unique in that they allow for plankton being based of a food web for a certain niche. So what we see here is from the figure from Vanote 1980 with the river content continuum. And what we see is as the stream size or stream order gets larger, there's a presence of phytoplankton and zooplankton present within these lotic systems, which makes it unique to allow this niche to occur within these systems. However, with this new niche forming in these larger streams, it allows an opportunity for invasive planktivore to take hold within these in this niche. So example of an invasive planktivore is dracaena mussels, and within the Great Lakes where they have invaded, they have caused major ecological shifts. However, in the large rivers of the United States, another invasive planktivore has been introduced, and that is the silver carp. And they're cyprinids from Eastern Asia. That were introduced to North America for biological control of algae and aquaculture ponds. And they have seen to have negative effects on native fishes, not just native planktivorous, but also native sport fishes through exploitation competition at earlier life stages. So the Illinois River is a river that is invaded by silver carp, and it's an important river for the invasion front for a variety of reasons. The Illinois River has a very large population of silver carp present within it, but it also has a series of hydrological connections that make it important. So the Illinois River connects the Mississippi River to the Great Lakes, to the Chicago area waterways. And through these connections, that could potentially allow for the movement and dispersal of silver carp from these large rivers into the Great Lakes. The Illinois River is also hydrologically managed, meaning that there is a series of locks and dams present within the river to maintain a certain water level to allow for navigational traffic of barges to move raw materials between the Great Lakes and the Mississippi River. But also, too, the Illinois River has a high habitat heterogeneity, meaning that there's a wide variety of different habitat types, such as backwaters and off channels that persist within the Illinois River. So the Wabash River is another large river that's invaded by silver carp. But the question is, how does the Wabash River differ from the Illinois River? How does the two invasion areas are different? So firstly, the Wabash River off-channel habitats tend to be more limited on this system. So there tends to be less side channels or backwaters is where they're more prevalent on the Illinois River. But more importantly, the Wabash River is free flowing, and this is going to change the way that the species might respond to conditions within their habitat. So what we see here in this figure, with gauge height on the y-axis in feet with month on the x-axis, the blue line represents average gauge height for that month within the Wabash River. So what we see is that the river pretty much drains throughout the year, and that the gauge height is relatively unstable with high variability in the gauge height throughout the year. As we're in contrast, the Illinois River in the yellow line shows a pretty stable system, and that gauge height does not change very drastically throughout the year. And through these changes, this instability in the Wabash, it leads to changes in gauge height. It allows for variable conditions that might allow for areas to become inundated or uninundated with water throughout the year. And that's what this figure on the right is showing. So the yellow polygon represents the area inundated by water in March, as where in contrast, the blue polygon represents the area inundated by water in October. So what we see from this figure is that area available to aquatic organisms within the Wabash could increase or decrease depending on the time of the year and gauge height. So kind of like the broad scale questions we're looking to answer through this talk is, how do invasive and native species react to temporal and spatial variabilities, and how do they interact with each other throughout these changes? But more specifically, in our first chapter, is how does a large river habitat quality change spatially throughout the year in an unstable system such as the Wabash River? And for our second chapter, how does a large river food web change daily in a more stable system such as the Illinois River? So wrapping up our broad introduction, moving into our chapter 1, which chapter 1 is going to be titled Habitat Quality of Silver Carp and Gizzard Shad within the Wabash River. So giving a brief introduction, gizzard shad are a native planktivore that have seen declines over the past 50 years within the Wabash River. And these declines have been independent of the introduction of silver carp. So silver carp are not the main driver of these declines. However, when sympatric with silver carp, gizzard shad have been seen to have decreased body conditions. So with the introduction of silver carp could add another pressure to the gizzard shad population that's already declining, which makes this a species of concern. However, between invasive and native species, they might respond differently to the variable conditions that persist within the Wabash. And that might allow for overlap of habitats occurring between the two species, therefore promoting competition between the two species, or it could allow for some habitat segregation, which would then limit potential competition occurring between the two species. So the objectives of this chapter are to, 1, determine how habitat quality changes throughout the year for silver carp and gizzard shad. 2, to understand the degree at which suitable habitats overlap spatially for both species. And 3, to assess if silver carp select for areas of habitat that are considered high quality. So like I said, the study took place on the Wabash River from its confluence to the Ohio River all the way up to Terre Haute, Indiana. And we sampled all the variable habitat types present within the study extent, including the 2 major tributaries, the Little Wabash that meets at New Haven, Illinois, and the White River that meets in Mount Carmel, Illinois. And we sampled our tributaries roughly 1 kilometer upstream of its confluences to assess the inputs and influences those tributaries have on the main stem Wabash. So for our sampling events, they occurred monthly between March and November 2022, and we collected a variety of bioconditions such as zooplankton, chlorophyll A for phytoplankton abundance estimates, and benthic detritus. But we also collected abiotic conditions such as water temperature, dissolved oxygen, and water velocity. So once we got back to the lab, we manually drew the river's boundary using ArcMap from satellite imagery provided by the USGS Landsat imagery program. And we did this for each month. So once we had the polygon manually drawn, we overlaid a tessellation grid pattern over the polygon to create these habitat cells as seen in the figure below. A full habitat cell, so the full hexagon, was 127 square meters. We then also wanted to estimate the conditions that were present within each habitat cell. So we did this by interpolating between our known sampling points using inverse distance weighted to estimate the conditions that were present within each habitat cell. We also then assigned each habitat cell with a habitat type, so such as like side channel, backwater, thowag, channel border, etc. To then see how those conditions persist in each of those habitat types. So what this figure is kind of showing is in the blue, it represents areas that are the channel border habitat, and then the yellow represents areas that are the main channel thowag. So just from this figure in this particular spot in time, we see that chlorophyll A concentrations were a little bit higher in the channel border than they were in the thowag. So we then, once we calculated or estimated the conditions that were present in each habitat cell, we then applied a bioenergetics model to each habitat cell. And we did this by grouping all 3 of our food types together to get available food resources. We then applied known filtration rate equations from both species to our available food resources to estimate the consumption that would persist within that habitat cell. We also added a dissolved oxygen parameter to our consumption equation to where dissolved oxygen fell below 4.0 milligrams per liter, consumption would start to decrease. We then subtracted energetic cost from our consumption equation, but we did modify our energetic cost equation slightly. More specifically in our respiration equation is we used water velocity measurements as a substitute for swimming speed, assuming that the fish was holding a constant position within the habitat cell. So through consumption minus energetic cost, we got growth rate potential, which then we used as an index for habitat quality. And so if the growth rate potential was positive, we considered that to be high quality habitat, as where if the growth rate potential was negative, we considered that to be poor quality habitat. And the masses used within our biogenetics equation varied. We modeled adults and subadults. So the masses for the adults were determined by using long-term monitoring electrofishing data collected by Eastern Illinois University within our study extent of the Wabash River. So we took average size adult silver carp and gizzard shad from that catch data to inform the masses we should use for adults for both species respectively within our models. As we're with the subadults, we wanted to create a mass that was realistic of that age class for both species, but we wanted to maintain the masses to be the same so that we could compare differences that were occurring between the two species. So now moving into kind of our results for our first objective, determining how habitat quality changes throughout the year for silver carp and gizzard shad. So firstly, I just kind of want to open up with the amount of area that was available to the organisms to use throughout the year. So on the y-axis, we have area in kilometers squared. As on the right y-axis, we have gauge height in feet. And total area is represented by the blue bars, and then gauge height is represented by the orange line, with the air bars being standard air. So what we kind of saw from this is the most amount of area available to these organisms was present within the spring, and that area started to decrease gradually throughout the year as gauge height started to decrease until it got to the fall to where gauge height reached its minimum within our sampling period, and so did the area. So now moving to the different seeing how much of the river was considered high quality habitat. So for the y-axis, we have percent of river, and how we did this was we calculated the area of the habitat cells that were considered high quality habitat, and then we calculated the total area of the river. So we divided the percent of, or the amount of high quality habitat divided by the whole amount of the river. On the x-axis, we have the months. The blue bars represent the area or the percentage of the river that was considered high quality habitat for silver carp, as where the yellow bars represent the area of the river that was considered high quality for gizzard shad. So this figure in particular is showing for the adults of both species. So what we saw was in the springtime, 0% of the river was considered high quality habitat for both species, as there was an intermediate amount in the summer, but still a large percentage of the river was considered poor quality for the both species. But in the summer, we see a pretty big jump in the percent of the river that was considered high quality for both species. And we see a very similar trend occurring with the subadults. Minus in the springtime, we see a slightly higher or a slight percent of the river being high quality for gizzard shad. But for the most part, it follows similar trends with very, very low being high quality in the spring, a intermediate amount, but still a low percentage being high quality in the summer, and where the river jumps up to being mostly high quality in the fall. So the reason why we're thinking this trends was in the springtime, we saw flooding, which allowed for increases of water velocity, which would then increase energetic costs. But there's also the water temperature was also pretty low, and the food abundances were also pretty low, which led to lower consumption. So with low consumption, high energetic costs, it kind of led to the majority of the river being poor quality. As we're in the contrast in the fall, we saw drought to where the river really slowed down to where there really wasn't a whole lot of water velocity present, which then lower energetic costs. With higher water temperatures and higher food abundances allowed for a higher consumption. So through higher consumption and lower energetic costs allowed for the river to be high quality. As we're in the summer, without the river flow is pretty much at normal flow, where food abundance and temperature was relatively pretty high for consumption. So you had a relatively pretty high consumption values, but you also had pretty high energetic costs due to the water velocity present within the system, to which would probably led to why the majority of the river was still considered poor quality habitat during the summer. So then we also wanted to look at which habitat types allowed for the best quality habitats. So on the y-axis, we have percent of habitat, and that was calculated the same way as the previous slide, except just grouping into total area of each habitat type independently. The x-axis, we grouped our months into different seasons. with spring being March, April, May, summer being June, July, August, and fall being September, October, November. We also grouped some habitat types together. So the blue bars are represented by the tributary habitats, and that's both the Little Wabash and White River tributaries together. The orange bars are the off-channel habitats, which are the side channels and backwater habitats. And the purple are the channel border habitats, which is the channel border habitat with the behind the sandbar habitat, and then the yellow is the thalweg habitat. So for adult silver carp, what we saw was the best quality habitats were off-channel and channel border habitats, and the worst quality habitats were thalweg habitats, which seems to be consistent with other invasion areas, to where on the Illinois and Mississippi River, off-channel and channel border habitats generally be associated with silver carp. So this might, and where the thalweg generally is seen to be where silver carp are not as present in those systems. So this might suggest that there are some similarities that are occurring between the different invasion systems. So moving to subadult gizzard shad, adult gizzard shad, I'm sorry. Off-channel and channel border habitats were also the best or high quality habitat, as where the thalweg habitat was considered the worst. With our subadult gizzard shad, the best habitat types followed the other two, to where off-channel and channel border habitats were the best, and where the thalweg habitats were the worst. But we see something different with subadult gizzard shad. So yes, the best quality habitats were off-channel and channel border habitats, but we do see in the fall the thalweg habitat was about equal to the tributary habitat, and where still a large percentage of the thalweg habitat was considered high quality in the fall. But also too, in the spring, we saw a very small percentage of the total river being high quality for subadult gizzard shad in the spring, which that then led to different habitat types also allowing for those for high quality habitat. So in the springtime, the best habitats for gizzard shad were tributary and channel border habitats. So if the survival or management of subadult gizzard shad is an important objective within a research project, maybe looking into these habitat types and making sure that subadult gizzard shad have access to these habitat types might be beneficial. So then moving to our second objective, to understand the degree to which suitable habitats overlap spatially for both species. So to quickly go over how we define spatial overlap, if the same habitat cell was considered high quality for both silver carp and gizzard shad, we considered that to be spatial overlap. As where if it was only high quality for one species and poor quality for the other species, we considered that it to be no spatial overlap to occur, and for the for that area to only be high quality for that one particular species only. And in this case, it would be the silver carp, and it would be poor quality for gizzard shad. So then looking at spatial overlap, on the y-axis, we have percent of river. On the x-axis, we have our months. The blue bars represent the total amount or the total percent of the area that was considered spatially overlapped. So this is the same areas that are considered high quality and for both silver carp and gizzard shad, as were any of the orange bars that are present represent areas that are percent of the river that is high quality for silver carp only, as where the yellow bars represent areas that are or percent of the river that is considered high quality for gizzard shad only. So what we see is that there's a high degree of spatial overlap occurring within the summer and fall. However, there are certain areas that are only high quality for gizzard shad, and there's like really just a small amount that's present within August, but we generally really do not see any percentage of the river that's high quality for just silver carp only. And we're seeing a very similar trend with our subadults, to where there's a high degree of spatial overlap occurring between the two species, but there is certain sections of the river that are high quality for gizzard shad only. So through these, this high amount of spatial overlap might suggest that there is competition occurring of high quality habitats between these two species. But because there's also sections of river that are high quality habitat for only gizzard shad only, Gittershack could potentially utilize these areas to escape competitive pressures inflicted by silver carp. So then we also want to see which habitat types allowed for the highest amount of spatial overlaps. So the same color scheme is from a few slides ago, with the same grouping of seasons from a few slides ago. So what we see for the adults, the habitat types that allowed for the highest spatial overlap were off-channel and channel border habitats, with the thalweg being the lowest. And we see very similar trends occurring with subadults to where the highest amount of spatial overlap is occurring in off-channel and channel border habitats, and the lowest in the thalweg habitat. So what this might further suggest that there is high competition occurring for high quality habitats, because the off-channel and channel border habitats were also the habitat types with the best, or were considered the best habitat types from our model. So moving into our third objective, to assess if silver carp select for areas of habitat that are considered high quality. So we wanted to first just kind of assess if the carp were actually using areas that we were predicting through our model performed in the study. And we looked to carry this out through a habitat selectivity index. So we surgically implanted 333 silver carp tags between 2021 and 2022 with acoustic telemetry tag. And they were actively tracked once a month by Dan Roth and Coy Blair from Eastern Illinois University, to where they were triangulated using a directional hydrophone. And once the fish was located, a GPS point was taken to mark the location of that fish within the river. We then apply a habitat selectivity index to where selectivity index is equal to X divided by Y times Z, to where X is the total number, or is the number of detections within the habitat type. Y is the total number of detections, and Z is the proportion of the habitat available. So looking at the results from our selectivity index, with selectivity index on the Y, with month on the X, and we only ran this analysis for months that had a high quality habitat present, because a organism cannot select for a habitat that does not exist. So the important thing with habitat or habitat selectivity index is the value of 1, and that's marked in the figure by the red dashed line. So anything above 1 or above that red dashed line indicates that the species was selecting for. Anything on the line or right at 1 means that it's a neutral selection, and anything below the line or below 1 means that they were selecting against. The numbers present on top of each data point represents the total amount of detections occurred within that month. So looking at our results, in June, we saw a selection against of our high quality habitats, and we think that this was most likely due to the low detection size or low sample size with the low amount of high quality habitat available. But in June or July and August, we see that there was a strong selection for high quality habitat occurring within the model or within the river. And then in September and October, we see more of a neutral selection for the high quality habitat within the river. And we think that this is most likely due to the large amounts of high quality habitat available, and coupled with the potential that active tracking data could bump fish to have them move to different habitat types. But when we combined all of our data together, what we saw was a slight selection for the high quality habitat predicted within the model, further suggesting that the adult silver carp were selecting for energetically high quality habitats present or predicted within the model. So moving into our chapter 1 conclusions for our first objective, to see how habitat quality changes throughout the year for both of these species. What we determined was planktivorous fish that inhabit the Wabash must be flexible to changing habitat quality. And we think water velocity plays a major role in determining the energetic benefit of these habitats, for the reasoning of in the springtime when water velocities were pretty high, We did not see any of the river being high quality, as we're in contrast in the fall when water velocities were pretty low. We saw a majority of the river being high quality. As we're in the summer where it was intermediate, but water quality was still pretty high, we still saw a large section of the river being poor quality. Our second objective is to see the amount of overlap that was occurring between the species. What we think, or one of our major conclusions, is that potential for competition is elevated due to the spatial overlap of quality habitats. However, competitive effects on gizzard shad might be lessened in select areas because certain sections of the river were considered high quality for gizzard shad only. And then our final conclusion for our third objective, to assess the silver carp, select for areas of habitat that are considered high quality. So we see, so our conclusion is silver carp did indeed select for energetically high quality habitats predicted within the model. So our management selections for our first chapter is, this may not be able to implement on the Wabash River because there's not a series of lock and dams, but on other invade areas such as the Ohio or Illinois or Mississippi River, we would be able to implement this. But on the Wabash, what we learned is that water velocity may play a major role in determining energetically high quality habitat for silver carp. So on systems that have a series of lock and dams, the dams could then increase water velocities to create poor quality habitat that would be present within the system for silver carp, but while maintaining water velocities that are not fast enough to still allow for high quality habitat of native species. But also too, with the selection, or in the Wabash, we did see that silver carp selected for energetically positive habitats through our model. So we could then continue to use our model to inform commercial or contract fishermen where silver carp are more likely to be, so that they could focus those removal efforts in those areas and to increase harvest. So wrapping up chapter 1, moving to chapter 2, and that is diode movements of riverine fishes and zooplankton. So diode movements are 24-hour movements of organisms within their environment, but this phenomenon is typically more strongly associated with zooplankton. And these movements are generally, or the mechanisms behind these movements are generally for predator avoidance, UV avoidance, or to increase foraging opportunities. But however, diode movements of fishes have also been observed within systems. And the likely mechanisms behind these movements are predator avoidance or to increase foraging opportunities. So diode movements of fish and zooplankton are pretty understudied in large rivers, and to understand how these organisms use and move between habitats within a 24-hour period is important for a variety of reasons, such as management of invasive species. If you know where the fish or the invasive is located at a certain time of the day, you could increase harvest efforts at a particular location at that time to increase harvest. It's important for accurate zooplankton sampling. So if zooplankton density is different throughout different times of the day, you may want to adjust your sampling methods to sample during when density is the highest, so your sample could actually reflect the densities that are present within the system. And then finally, it's important to understand how organisms interact with each other within a 24-hour period to further understand the ecology present within these large rivers. So that leads to my chapter 2 objectives. The first one being assess if there are any diode changes in zooplankton density for 3 of the 3 major taxon, and those taxa being Cladocera, copepods, and rotifers. And our second objective is to assess if fish habitat usage varied diurnally. So like I said, the study took place on the LaGrange reach of the Illinois River, and we selected 3 different sampling locations present within the section of river that had a main channel and adjacent off-channel habitats. So in one of these sampling locations, this is a blown up picture of what one of these sampling locations might look like. We see that we have the off-channel that's represented by the yellow polygon, and the main channel that's represented by the blue polygon. To where the red triangles represent areas of main channel zooplankton sites, as where the green circles represent areas of off-channel zooplankton sites. So field sampling occurred in October 2018 by SIU and the Illinois River Biological Station, and sampling occurred every 4 hours within a 24-hour period. And we sampled fish density using mobile hydroacoustic survey through a transect that encompassed all 3 zooplankton sites. The downside, though, to hydroacoustic surveys is that you cannot determine species composition from your hydroacoustic data. So shortly after the transects were completed, a crew was sent out to get species composition within the river using a variety of sampling methods such as gill nets or electrofishing to avoid any gear bias. We then were able to use the species composition to inform our hydroacoustics data to estimate densities of each species. And then to be in sync with our hydroacoustic surveys, zooplankton sampling occurred at the same time. And zooplankton surveys were conducted using a battery-powered diaphragmatic pump with a weighted hose, to where sampling occurred at the surface and at the bottom. And we used 2 different sieve sizes. We used a 55 micron mesh for our larger bodied zooplankton of cladostrid and copepods, and we filtered out 30 liters of water through that mesh size. And then we used the 25 micron liter for our smaller bodied or for our rotifers, and we filtered 10 liters of water through that. And then in conjunction with each zooplankton site, environmental data was also collected at the surface of the water. So to analyze our data, environmental data was analyzed from water temperature and water velocity, and we use a general linear mix model for this portion of the equation. For zooplankton, we modeled rotifers, copepods, and cladostrid. But I also want to make it important to note that we did model each habitat type separately. So we modeled the main channel rotifers separate from the off-channel rotifers, and etc. for the other 2 other taxas. And we use this using a generalized linear mix model. And then for our fish densities, we had 2 groups of planktivorous, which were silver carp and our big mouth buffalo, as where non-planktivorous would maybe be like your river carp suckers, other suckers, catfish, and etc. And we used a generalized linear mix model for this, but we also employed a likelihood ratio test to assess if the interaction term was what was driving our models. So getting into our chapter 2 results for our first objective to see if there are any diurnal changes of zooplankton density for the 3 major taxa. But firstly, I'm going to go into our environmental results. So on the y-axis, we see water velocity in meters per second, as where time is on the x-axis. So the main channel water velocity is represented by the blue line, as where the average for each time, and the off channel is represented by the red line, with the air bars being standard air. So what we saw through our model is that there was a habitat type effect. So that the main channel had a higher water velocity than the off channel, and we did not see a time effect. So water velocity did not vary throughout different times of the day. As we're with water temperature, we saw a little different story, with water temperature being on the y-axis in Celsius, time being on the x-axis, and we're following the same color scheme as the previous slide, and the air bars are still standard air. We saw a habitat and time effect. So the off-channel habitat had a higher water temperature than the main channel, and there was a time effect, meaning that water temperature in both habitat types were higher in later afternoon and in the evening than it was in the morning. So moving into our zooplankton results, I'm only going to show data for the models that showed any significant effects. So that the only two models I'm going to show are off-channel copepods and off-channel cladoceran. So I'm not going to show off-channel rotifers or all three taxes in the main channel, and that's because, like I said, none of the effects came out to be significant, suggesting that there were not any diode movement occurring within these taxes in those habitats. But in off-channel copepods, what we see is density on the y-axis in numbers per liter, with time on the y, with the yellow bars representing the copepod density at the bottom, as where the blue bars represent the copepod density at the surface, with the air bars being standard air. So we saw a time and depth effect for off-channel copepods, with the bottom depth being a higher density than the surface. But the main effect we saw was with time, to where copepod densities were higher at night than during the day. And we're seeing a very similar story with off-channel cladoceran, except we only saw a time effect. With the same color scheme as the copepod graph above, what we saw was cladoceran densities were higher at night than they were during the day. So then moving to our second objective in our chapter, to assess if fish habitat usage varied diurnally. So for our planktivore fishes, we see fish density on the y-axis in numbers per 1,000 meters cubed, with time on the x-axis. The density of planktivores present in the off channel is represented by the purple bars, as where the fish density of planktivores present in the main channel is represented by the yellow bars, with the air bars still being standard air. So through our likelihood ratio testing, we saw that the model was best explained by the habitat type time interaction term. But through post hoc pairwise comparisons, we saw that the off-channel planktivore density was higher than the main channel, but we did not see a time effect. So planktivores were just kind of hanging out in off-channel habitats and not moving between main channels. So there wasn't a horizontal movement of habitats throughout the day occurring for planktivores. And a very similar pattern occurred in our non-planktivore group, to where the model was also best explained by the habitat type time interaction, and through post hoc pairwise comparisons, we saw a very similar pattern to our planktivore species, in that the off-channel habitat had a higher density than the main channel, and there also was not a time effect, also suggesting that non-planktivorous fish were not moving between the two habitat types throughout the day. So with zooplankton, or larger body zooplankton, moving in the off channel, that then leads to the question of what caused zooplankton diode movements. So an initial thought is UV, and zooplankton have seen to experience diode movements to have UV avoidance, because UV rays can cause damage to tissues and lead to mortality in zooplankton. However, UV does scatter in very turbid rivers, or in turbid waters, and the Illinois River is very turbid. So for this reason, we do not think that the UV would have much of an impact on zooplankton within the Illinois River. For this reasoning, we do not think that UV avoidance was the likely mechanism that caused the zooplankton movements. However, another mechanism could be predation, and I think the cases that might support this is that we observed the strongest swimmers to move. So our off-channel cladoceran and copepods were the only two taxes to move, and these are generally associated with your stronger swimmers, to where the rotifers are generally associated with weak swimmers, and we did not see any diode movements within those taxes. So the only zooplankton that moved would have the capability of avoiding predation. But also too, silver carp are the predominant planktivore within our study. And silver carp have been seen to cease feeding at night, where peak feeding is during the day, which kind of is in sync with our zooplankton densities, to where we saw the densities of zooplankton the lowest during the day to where feeding would probably be the highest, and then the highest densities of zooplankton at night to where feeding would probably be the lowest. So what that would potentially allow for movements of the zooplankton to come out of the sediments and into the water column to exploit other life history traits or foraging opportunities. So for these reasons, we think that predation was the likely mechanism that was causing the zooplankton movement into the water column. But with zooplankton also moving into the water column, it leads for this potential of a downstream drift or transport of zooplankton, because even though water velocity was still lower in the off channel, there was still some water movement that occurred within this habitat type. And zooplankton have been seen to exhibit drift in other systems. However, this phenomenon is largely associated with larger invertebrates such as aquatic insects, and the benefits to the insects would be to replenish diminishing downstream stocks or to move to high quality habitat. So future studies should take this into the downstream drift of zooplankton into consideration, or to look further into this phenomenon in future studies, and determining whether is it active or passive, and if active, what would be the potential benefits or the potential drawbacks to entering the drift. So our conclusion, our chapter 2 conclusions for our first objective, to see if there are any diel changes of zooplankton density for the 3 major taxa. We saw that movements were taxa specific, and that the larger bodied zooplankton were the only ones that exhibit diel changes of behavior in the off channel. And that we think that predation response was the most likely mechanism. And then for our second objective, to assess if fish habitat usage varied diurnally, we did not see any diel changes in habitat type, with the highest densities occurring in the off channel. And because of this, we say that off channel habitats are an important habitat type for the fish communities within the Illinois River. So our management implications for our second chapter is to maintain or restore the connectivity from the main channel to off-channel habitats. And we're saying this for a variety of reasons. One, our data kind of support that the environmental conditions in the off-channel are less harsh than the main channel, meaning that water velocity is lower, but water temperature is higher. So this would allow for energetically higher quality habitat to occur within these habitat types. And second, our highest density of fish and zooplankton occurred within the off channel, so these habitats are important to these biota. But then lastly, we did see this unique set of interactions only occur in the off channel habitat as we're of diel movements of zooplankton. So to allow for these predator-prey relationships to play out within large rivers, it will be important that these habitat types are available for both of the biota to utilize within these large systems. So kind of wrapping up chapter 2, getting into our final conclusions. Our overall conclusions are that large rivers change energetically throughout the year, and this then alters quality habitat availability throughout the year for the planktivorous that inhabit these systems. Environmental pool management could be used to help manage silver carp by altering the hydraulic patterns and then in turn habitat quality. Off-channel habitats in large rivers allow for unique biotic behavior, and maintaining these habitat connections are important to allow for these interactions to continue to persist. And fish habitat quality in large rivers can vary from sub-daily to seasonally. So with that, I would like to thank the following people: Dr. Jim Garvey for taking me on as a mentee and serving as my mentor through the grad school process. I'd also like to thank Dr. Dave Coulter for his time that he put in helping me troubleshoot any issues with the project. I'd also like to thank Dr. Charlotte Nart and Dr. Thorpe Halloran for their assistance in serving on my research committee and just pouring into me and helping me grow professionally in my fisheries career. And then Justin Kowalski, McKenna Goldtrap, Octavio Slavia, Aaron Crone, Hannah Hornquist, Adam Johnson, Jacob Beer, and Lauren George for all their assistance in helping collecting field data. And then special thanks to McKenna and Lauren for their help processing zooplankton within the lab. I'd also like to thank EIU, specifically Dan Roth and Coy Blair, for their assistance with active tracking data, but then also providing the long-term monitoring data to inform the mass estimates for my biogenetics equation. And then the Illinois River Biological Station for their assistance and support for our second chapter on the DIEL chapter. So thank you again for taking the time to listen to my talk. And with that, we'll leave it to any questions. Thank you.